For this next little section, I did some cooking show magic, and I kind of baked some of the writing of the lecture ahead of time because it was kind of writing heavy, and it didn't seem like an efficient use of lecture time to be, writing all of this information. So I'm going to kind of talk you through what we're doing, and do some fill in the blanks, right? Um, so what we're talking about here is the transformations of functions, right? And hopefully this section is payoff of what we did last week, where we sort of looked at the like archetypes of functions, right? Like all of the power functions, all of the root functions, all of that. Our function transformation rules allow us to take those parent graphs, mess with them, and still graph them with relative ease, right? And we're going to make use of a little bit of this idea of graphical addition on it, right? So the first thing that we're going to look at are these vertical transformations, right? Ways that we can shift a graph vertically, right? So suppose we have some c greater than 0, right? Some positive real number. If we add that number to our graph, what that's going to do is it's going to shift it vertically by c units. It's going to shift it c units upward, right? So what that means is that, say, at every point, we're going to move our graph up c units to obtain a graph that looks something like this, and that's going to be f of x plus c, right? Similarly, if we were to say subtract c units, that would mean that at every point, we're going to shift our function down c units, right? We're going to shift it downward. And it's worth noting, right, that like my graph of f minus c and my graph of f of x, it's not a perfect shift, because my hand is not perfect. But in, this like ideal math world, it would be perfect, right? So let's do two little examples on this parabola, right? So if we're going to shift it up 3 units, what that means is that each of these points of the parabola gets moved up 1, 2, 3 units, right? This allows us to very quickly graph x squared plus 3 without having to consult a table of values, right? Just transforming the function that we already know, right? So now if we're doing, say, x squared minus 2, we're going to shift everything down 2 units, and we're going to get something like this, right? So adding on to the end, right, adding that constant moves our graph up and down. For the next one, right, let's say we're doing horizontal transformations. Okay, so once again, we have some c greater than 0. What happens if we, say, do our function, but everywhere we see an x, we write an x minus c, right? What this has the effect of doing is it actually shifts our function c units to the right, right? Because for every point, you know, um, on the x-axis, well, we subtract c from it. So we get a different input value, but the same output value that it would have been, right, without that c. So we're going to shift to the right, okay? So that's f of x minus c. Similarly, if we say add some positive real number c, we're going to shift to the left, right? So over here on this graph, we're going to do something like this, where this purple is f of x minus c. Going back down here, we're going to start with the same parabola. Okay, so let's say we're, doing g of x is x minus 2 squared. Well, that means that every point on this parabola gets shifted 2 units to the right. 2 and 2. And I guess we have ones up here, so we'll go 2 and 2. So we can connect all of these dots with a continuous, smooth-ish line, right? And now if we're doing h of x is x plus 3 squared, that has the effect of taking x squared and shifting it 3 units to the left, right? So we have 1, 2, 3, 1, 2, 3, and then 3 units, and so on and so forth. And we do our best for that smooth line, a little something like that, okay? Now we have a like bigger example, right? So let's find and graph this, right? So what this is going to do, right, as a transformation, is we're going to take our graph of the square root of x, we're going to shift it 4 units to the right, and then we're going to shift it 3 units up, right? So let's do those sort of one at a time, right? Let's say first do this, let's shift it 4 units. We go 1, 2, 3, 4. 4 and 1, 2, 3, 4. So this is step 1, right? This green graph. This is the square root of x minus 4. And then now to get our plus 3, all of these points get shifted up 3 units. A little something like that. And we have our final graph of x minus 4 plus 3. Okay. The next idea are reflections, right? So what happens if we're multiplying by a -1 somewhere, right? So our first one, what if we do our function and then multiply by -1? Well, what that has the effect of is we're flipping the whole graph around this x-axis, right? Because any point, we actually get the negative of it, right? So we're going to get something like this, okay? And we're going to reflect it along the x-axis. I might have said y-axis earlier, but we're doing this around the x-axis, right? Because when we take the negative of the output, it flips it there, okay? What if we take a negative on the input? Well, that's going to have the effect of reflecting it along the y-axis, right? Because if we have some input here and has an output here on the negative, well, if I input the negative instead, that's going to reflect along the y-axis. Okay? Next up, we're stretching, right? So say we have some real number c. We have two cases here, right? We have c is greater than 1, then we have c is between 0 and 1, right? If c equals 1, well, then there's no effect to the graph, right? Because we're multiplying our whole function by that constant. And if c is less than 0, right, if c is negative, what that means is we're going to get one of these effects and then a flip about the x-axis, right? So we can only work with these two cases, okay? So if c is greater than 1, well, then at every point we're multiplying by some constant, so we're going to stretch the graph by a factor of c, right? If this is our function f, every point is going to get stretched by a factor of c, okay? So that's c times f of x, okay? Now, what if c is between 0 and 1, right? What if c is, say 1/2 or 1/3? Well, then that's going to have the effect of shrinking our graph, right? Because whatever the height is, we're multiplying it by 1/2, so it's going to get shorter. So we might do something like that, right? That would be c times f of x as well, right, for some, small value of c. Up next, we have a couple more examples, right? So once again, we're starting with our parabola. And we're gonna first look at what happens when we, stretch it by a factor of 2. Well, what that's gonna do is like everything is gonna get steeper, right? So this point here has a value of 1, so now it has a value of 2, right? These guys are at y equals 4. They're now going to be at y equals 8, which is off the page, right? So our graph is going to become something like this. It looks just like our original parabola if we were to just, stretch it a little bit vertically. Now say we're dealing with this red function, right? H of x is a third of x squared. Well, that means that every point is going to get shrunk down by a factor of 1/3. Our points at 1 are now going to be at 1/3. Our points at 4 are now going to be at 4/3, which is going to be just over 1, right? It's going to be 1 1/3. And our points at 9 are now going to be at 3, right? Because 3 squared would normally be 9, but we're taking a third of it. So it's going to have an output of 3. And this is enough information for us to get our parabola. This parabola looks just like our, parent parabola, but as we've said, it's kind of shrunk down a little bit. Next, we'll take a look at this example, right? As we see from this x squared right here, right, our prototype graph, our parent graph, is this parabola. And we're going to do things to it sort of one at a time, okay? First, we're going to move it 3 units to the right, right? That's what this x minus 3 is. So we'll grab our red color first, and we'll move it 3 units to the right. Okay, so that's going to look a little something like this. Okay. Up next, we're going to multiply it by -2, right? So that's going to have the effect of flipping it downward and stretching it by a factor of 2. So that's going to look a little something like this, right? And then our final action is we're going to move it upward by 1 unit, which I guess I'll switch to blue, moving it up by 1 unit, which is here. And each of these points move up by 1 unit. And we get our parabola. This is the graph of f of x is 1 minus 2 times x minus 3 squared, okay? We have one last sort of topic that, kind of gets smushed into this, right? We've looked at how these different functions, these parent graphs are transformed, and we have two kind of broad classes of functions that I just want you to be aware of, okay? And they're called even and odd functions, okay? And they follow the following rules, okay? So f is even if f of negative x equals f of x, okay? Now, why might this be a useful definition? Well, one of the prototypical even functions are even powers of x, right? So something like x squared. If you feed in a negative x, well, you still get x, right? So x squared follows that, x to the 4th follows that, and so on, right? So an even function, one of the nice things about it, since flipping it along the y-axis doesn't change it, well, that means that it needs to be symmetrical about the y-axis, right? So maybe something like that, right? If you were to flip this way, nothing's going to change. So now odd, as you may guess, is inspired by our odd powers of x, right? I'm not saying that f of negative x is negative times the f of x. And the um, sketch for this is slightly less intuitive. Um, Essentially, what it's saying is that we're symmetrical about the origin, right? So if you flip it on the x-axis, that's the same as flipping it about the y-axis, right? So that might look like something like this. When you consider it like around the origin, it's symmetric, okay? So let's do a couple of these examples and we can finish up this lecture. I know it's gone a little bit long. So we're just determining if the following functions are even, odd, or neither, right? And the way to do that, right, is to consider f of negative x. Well, f of negative x is negative x to the fifth plus negative x. As we've said, these odd powers of x are odd functions, right? So that would mean that negative x to the fifth is the same as negative x to the fifth, right? That's a small distinction, but here our negative is raised to the fifth power. Here it's not, okay? And that's minus x. But notice that I can factor out a negative 1 and get x to the fifth plus x, which is negative f times x, right? So this is odd, which is great, okay? What about b, right? What's g of negative x? Well, that's negative x to the fifth plus negative x to the fourth, and that's going to be equal to negative x to the fifth, but that's just plus x to the fourth. And unfortunately, we can't do anything more here, right? We can't factor out anything in order to get a g of x, so this is neither. Finally, let's consider h of negative x, okay? Well, that's going to be 1 minus x squared minus a minus x squared, right? That minus x squared is just going to be an x squared, right? So that's already equal to h of x. So we're even, right? One interesting thing to note here, just kind of for your own benefit, this constant function 1, also an even function, okay? So with that, that's going to sort of wrap up our look at these, types of graphs and all that. There's one more lecture before we finish all of chapter 2 and have covered all of the content before the test.